Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 23, 2025, which was about 4 days ago. The standout result is a plug-in exploration module that keeps robot actions on a learned task manifold, delivering smoother motions and up to 50.8% average relative improvement after one round of self-improvement. The paper is titled SOE, Sample Efficient Robot Policy Self-Improvement via On-Manifold Exploration. And as we will see later, the gains extend across simulation and real robots. In short, the method learns a compact latent space with a variational information bottleneck, proposes safe diverse actions, plugs into diffusion policies, and even supports human-guided steering. Alright. The previous segment set up the promise of on-manifold exploration. Figure 1 contrasts off-manifold exploration, which causes unstable jerky motions, with on-manifold exploration that keeps actions structured and efficient. The left panel illustrates erratic paths near a toaster, while the middle panel shows smooth, coherent trajectories to the same goal. The right flow diagram then links exploration rollouts with demonstrations through imitation learning, so the policy updates safely and improves over time. Well, Figure 2 introduced the contrast. The previous figure showed outcomes, and Figure 2 shows the dual path setup that makes exploration safe and useful. The top path runs the base policy, which sends an observation through an encoder and into the action decoder for stable execution with an imitation loss. The bottom path forms the exploration module, which encodes to a latent mean and variance, samples a latent, and decodes actions under a bottleneck loss. Separate gradients keep stability while enabling diverse proposals. The previous figure outlined a dual-path design that keeps exploration stable. Figure 4 compares action proposals across 3 methods on a mug task. The left column with DP shows nearly identical short trajectories that repeat failures. The middle column with SIME spreads widely but creates tangled, jittery paths that are temporally inconsistent. The right column with SOE focuses proposals toward the mug with smooth, coherent arcs, which signals on manifold, purposeful exploration. So while Figure 4 highlighted proposal quality, Table Y reports real-world outcomes across 3 tasks. The exploration module raises pass at 5 to as high as 1.0 on toaster load, lowers average jerk versus SIME, and cuts rollouts to roughly 30. Success rates climb strongly. Steering reaches about 62% relative improvement on lamp cap and 50% on toaster load, while the basic diffusion policy even drops on mug hang from 0.47 to 0.38. So, while the previous table quantified real robot gains, Figure 6 shows success rate over rounds in 4 simulated tasks. The plots indicate that the exploration module climbs steadily across Lift 10, Can 20, Square 20, and Transport 20, whereas diffusion policy and SIME behave inconsistently. Lift 10 nearly saturates by round 2, and Can 20 and Square 20 rise cleanly. Transport 20 improves smoothly, while SIME plateaus. Shaded bands mark variability across runs. Alright, 2 takeaways stand out. Constraining exploration to a learned task manifold yields safe, smooth, and diverse actions, and the plugin module improves success markedly, about 51% in one round, without hurting the base policy. The broader implication is faster, safer robot self-improvement with optional human steering, practical for real deployment. Thanks for listening. I am Alex. That is it for this episode of the AI Research Roundup.